Welcome back from lunch. Hopefully, we all met some people, had some good discussions. Lia Yeh from the University of Oxford, whose PhD is currently under review. So we're all is going to give us a talk on making the quantum world accessible through quantum picturalism. Take it away, Lia.
Hooray. Thank you, Justin, for organizing this, and thanks, Thomas, for the really excellent presentation. I got so excited when I saw that you were presenting first, and then Justin sent me your slides on last year, so I based what I would present based on that, so that it would continue off. So, I'm currently about me, because you'll be listening to me for 1.5 hours. I've just finished my 5th year and final year of doing PhD in the computer science department at the University of Oxford, and I thank the Google PhD Fellowship for funding the last 2 years of that. And I'm also finishing my 3rd year working half-time as a research scientist and engineer at Quantinuum, which is, I think, the world's biggest quantum computing company by number of employees. Most 2/3 of whom are scientists, more than that, 70%. And before that, I'm from California, so I'm really happy to be back for this. I did computing and physics double major in the College of Creative Studies at UC Santa Barbara. Here's the roadmap of this tutorial. So I'll start with an introduction, just big picture about pictorial reasoning. And then a tutorial on the ZX calculus, which is a graphical formalism for researching and teaching quantum computing and quantum information. Then I'll say a bit about our study where we taught high school students using the ZX calculus and pictorial reasoning. And finally, I'll do an activity, a short activity. We'll see how far we get. And a bit of whiteboard extra stuff if we have time. So this is, I guess, not the main thing I wanted to go over today, but I think that this helps. Commonly, so I always try to squeeze in a bit of looking at quantum computing hardware in history versus classical computing hardware in history whenever I introduce quantum computing. So I guess where quantum computers are now is kind of similar to where classical computers were in the 1950s. So in the 1950s, you have a classical computer, it takes up the entire room, and at some point the head of IBM said, we'll never have more than 6 classical computers in the whole world, and it was clearly the very wrong bet. And so what I'm interested in, I guess, my research is generalizing what you can do with quantum computers. So instead of programming in zeros and ones, I'm interested in this write once, run anywhere kind of idea for quantum computing, where even if you have many different hardwares, you can still be able to write quantum programs and verify that they're correct, and compile from algorithms and error correction and hardware all throughout the quantum computing stack. So this would be really out of date if this was classical computing, because this was the slogan of Java in the 1990s. But in quantum computing, this is a really fresh idea that it hasn't been realized yet. So we'll see that coming next if you kind of follow the history of classical computing. So today's classical computers now have this quite mature stack where at the bottom you've got semiconductors as the hardware, and then you've got algorithms on top, and people have figured out the different modules and layers in between. But in quantum computing in 2018, it was just we have these qubit implementations and the algorithms we want to run, and this gigantic gap in the middle of what we think should go there. And in 2018, quantum computer science people would look at this and say, oh, well, it's okay. In a few years, we'll have a better idea of the hardware, because there's a few different qubit implementations. And we're now about 6 years later from that. And now there's even more hardware implementations of quantum computing than we had in 2018. So this kind of idea that the quantum computing hardware would mature more, and so that we'd have a better idea of how to build a stack. Now we've got many different stacks for the different hardwares. So from the quantum computer science, or I guess in terms of technological progress, then the idea is, well, it's not okay. We have even more hardware platforms to deal with than before, so how do you compile to all the different ones? And interestingly, these are different silos is an analogy brought by the Unitary Fund nonprofit, which is advocating for open source in quantum computing and quantum information. So they said that this is like silos because each hardware has its own quantum computing stack thinly sitting on top of it. But these silos are kind of separate from each other. They don't really talk to each other much. And they said that this is kind of no single stack is like kind of fragile. They're not robust enough to go the distance. So the kind of way that quantum computing would be trending is to go towards a rich ecology where you have different cross-platform, like cross-quantum programming language, open source software capabilities across the quantum ecosystem. So we're kind of seeing more of that as we're going through the recent years in quantum computing. So the more mature stack, I'm currently working on a kind of a perspective paper effort to try to describe all these different more mature stacks. So the gap is now more narrow, and we have the hardware growing from the bottom to the top, and then we also have the software and algorithms going from the top to the bottom. But they still haven't met in the middle yet. So the biggest gap in the middle is quantum computer architecture and error correction and how they work together. So that's like the current status of things. But most of this presentation is going to be about drawing diagrams and pictorial representations to both represent and calculate quantum information in computations. So, and the idea is that these representations will also let you more abstractly reason in higher levels of the stack, so instead of always working with zeros and ones. So here is a Feynman diagram, a Feynman loop diagram, which 1965 Nobel Prize in Physics was awarded to Richard Feynman for creating a new quantum electrodynamics, contributing to creating a new quantum electrodynamics by introducing Feynman diagrams. And also in, say, computer science, you also have diagrams used to represent these kind of for example, languages in automata. Maybe the closest to the kind of quantum diagrams we'll see today is by Roger Penrose, who won the 2020 Nobel Prize in Physics for proposing critical mathematical tools to describe black holes. So these are tensors where you have inputs and outputs to each tensor. So this, for example, the top left Q sub FG and then superscript ABC is some process which has F and G as inputs and ABC as outputs. So those types. This is a common debate around people teaching quantum computing, where do you start from as the classical entry point. I'll talk a bit more about the physics entry point in a few seconds, but I think in a few seconds. But for computer science, a common popular approach is to start with binary operations, so like XOR, addition, subtraction, these kind of things. So you can visualize those kind of XOR and different kinds of classical bit circuits. And more generally, you can also just do this with any numbers that has some arithmetic operations on it. So we can represent processes that are being computed with, let's say, you wanted to represent 3 minus a plus b divided by x. And you could represent it with this diagram, which is taking a plus b, and then that thing is divided by this input, some open variable. So it's an open wire input called x. And then that thing is 3 minus that thing, and that's your output, which is y. And it turns out this is extremely useful as a conceptual building block for understanding quantum computing. So something you really commonly see is this parity operator, or this plus or x observable, basically, where this is, you can generalize it instead of addition only having this many inputs and then one output. You can also just say the sum of all the inputs is equal to the sum of all the outputs. So that would be this generalization of the plus operator. So I guess process theories would be, I guess you could formalize these in category theory, but you don't need category theory to define or understand them. So it was just historically where it came from. But then you can look at processes formalized in terms of the boxes and wires. So each wire has a type. And then these boxes take 0 or more wires as input and output 0 or more wires. So you can compose these boxes and wires as a way to like mentally arrange, as well as you can draw your processes. So for example, strings on wires on the top, you could like slide those boxes along the wires. And you can also compose in parallel. So F tensor G and that thing tensor H, which since tensor product is associative, you could also just draw it without any parentheses like that. You can also compose in sequence. And so just like with both tensor products, so parallel composition and sequential composition, so like if these are matrices, think like matrix multiplication, these you can compose also without parentheses and just draw it like this. And so implicitly, whenever you draw quantum circuits, these are already the mathematical properties that are satisfied by your circuit diagrams, but you can do a lot more with them. So with quantum processes, this is kind of a helpful conceptual way to think about and draw your processes. But if you represent them as like based off the number of inputs and outputs, then states are things with 0 inputs and 1 or more outputs. Maps are things with 1 or more inputs and 1 or more outputs. Effects, so like think bras to the corresponding kets, so just like think row vectors instead of column vectors. These effects are 1 or more inputs and 0 outputs. And scalars are just some complex number. These things have 0 inputs and 0 outputs. So you can compose them, for example, any normalized states. So this just means that this is a physical state because the probabilities of all the possible outcomes that you did a measurement, any kind of measurement for, would be added to 1. So like a normalized ket psi state, if you take the inner product with its corresponding like conjugate transpose that effect, then you get the number 1, which is equal to just empty space, because you just, if you multiply anything by the number 1, or tensor product by the number 1, it's still that same thing. So I guess a big picture slide that I've here borrowed from Austin Fowler from Google Quantum AI, he posted these slides publicly. So this slide he wrote, if you are working on a quantum compiler, we don't need this, a logical quantum circuit. We need this, which is a simple ZX calculus graph. We'll make this, which is lattice surgery. So they had some automated, they automatically compile these like very complicated looking 3D diagrams for quantum error correction. And they'll run it on their quantum computing hardware, which is in California. So in this talk, I'll mostly talk about the ZX calculus, which is a formal graphical language invented in 2006 by the group I'm doing PhD in the Department of Computer Science at the University of Oxford. So we're kind of seeing that this is kind of gaining popularity across mostly quantum industry as well as academia as a way to do quantum computing research. So I would say at least the top 4 like biggest employers in quantum computing industry, which like Quantinuum, Google, IBM, and PsiQuantum, I think, are using this ZX calculus in their like research papers. So it's interesting as a skill. This slide here is my kind of side comment about instead of computer science like entry point via classical circuits, Boolean circuits, and like and or not logic, you could also take a physics approach. So if you have students that are comfortable with linear optics and like say operations on photons, then you could also draw diagrams to formalize those operations as well. And this is like at the quantum architecture level, but you could like zoom in onto these different components. Like this is a stream, which is like at time step this, you do this, and then at the future time steps, this is a recursive definition of what is the process being done. But this is a entangled photon emitter, one way to emit entangled photons in photonic hardware. And you could also decompose these measurement modules. Like if you zoom in, then these are linear optical circuits. So those are like beam splitters in the middle there. This is my, oh yeah, here. So that's a beam splitter. That's a phase shift, and so on. And these are like, oh, actually, I have the slides. Yeah, beam splitter, phase shifter, and photon detectors. So you can connect it to physical hardware. So for more physically motivated students, like if physical concrete examples are more motivating to students, this is also a way that you could start getting them excited and introduced to quantum computing hardware. So yeah, that's the first part. The second part is a tutorial on the ZX calculus. So I will mention we do have a high school course for this that we did a study on. So that's like a YouTube series. So this will kind of quite condense that. So it won't go as far, of course, but so we'll go a bit at speed. But I'm grateful for Thomas's introduction before this, which helps you see the bracket notation. So I guess essentially the ZX calculus, you draw all your diagrams and you've only got two types of building blocks. And every diagram is made of just like sequential and parallel composition of these two things. They're called spiders because they look like spiders. They've got 0 or more legs that are input or output. And essentially they're called Z and X because they're diagonal in the Z and X bases. So this is the thing in the, we'll show the block sphere in like a slide or two. So a diagram in the calculus is an undirected graph where every vertex is one of these two things. So Z, which is conventionally green or lighter colored, and then X, which is conventionally red or darker colored. Although I might use pink at some point. So the undirected part is really unique to this because only the connectivity matters. So it's a more flexible language where you have the ability to represent processes in space-time because some flexibility with that, which is a kind of uniquely quantum property of computation. So this equality here means that if you were to write down the matrix that the left-hand diagram interprets to, also write down the corresponding matrix that is represented by the right-hand side, then these are the same matrix. So this equal is like this matrix is equal to this other matrix. And so instead of writing down these exponential sized matrices with a number of qubits, you can just work with these diagrams. So you can write down any circuit like this, but you could also write down like other processes like quantum communication protocols, which we'll see later in this presentation. Yeah, no. Oh, yeah, the book is from 2023. So I'll show the book, which is like the textbook we used for the high school study in a few slides. But this was the original paper from 2007. Oh, okay. But yeah, so this is like the research paper, and then the book is like the second or third textbook about that.
I think we're learning so much every year. I'm trying to remember like what we already know or what we have already heard as opposed to something similar but different. So thank you. This is good.
Yeah, it's good to make the connections. So only the connectivity matters. If you look at these two diagrams, they're the exact same, except you can like bend and squiggle and cross over the wires as much as you want, as long as ultimately what is connected to each input and what is connected to which other nodes in the graph is all the same. You can move things around.
You're saying that corresponds to two matrix multiplications? And then how would you know what order to multiply the matrices?
Yeah, I guess when you choose a matrix multiplication, you're already implicitly prescribing an order because you could like chop vertical slices across this, and each slice could be some matrix. So that would implicitly assign an order. And then those associative properties shown before means that in those associative cases, it doesn't matter what those order of operations are because any choice would be the same. So you could just say always do it like sequentially, for example. But the choice of these slices will physically correspond to something very different. So you could have many different physical processes that do different things at different times or even involve classical communication, and that would mathematically be the same matrix, so the same quantum computation. But then the order of operations means what operation you're doing at any time step. So that's So that's a really good question. So for example, this stuff, like this physically can implement any quantum computation that you could do on a circuit-based quantum computer. But this is measurement-based quantum computing, where you're compiling things that are like repeated at every time step, but you could still prove that this does the same computation as a circuit-based quantum computer, where you're doing like a gate every time step. So, so it's quite exciting. Oh yeah, so that was universality, which is the idea of universal quantum computation is that any quantum computation, so any matrix, a complex number matrix that's like, that computation could be realized by such a quantum computer. And so anything on any number of qubits can be done with these diagrams. Can be represented with some diagram made of just those two things. And so, but actually what this translates to, like in terms of qubits and gates and measurements, so single qubit basis states, so the Z and X basis states, the Z basis or computational basis states are just the ones that you call your bits, so ket 0, ket 1. And the X basis states are ket plus and ket minus, so the things at the plus and minus ends of the X-axis on the Bloch sphere. And so here's drawing the Bloch sphere. And so this one input, one output green rotation of angle alpha. That green Z phase gate, that's a rotation about angle alpha about the Z-axis of the Bloch sphere, so this thing in green. And for the X-axis, then the X rotation about angle alpha would be like this X-axis in pink down here on the bottom. So this is the same Bloch sphere as in Thomas's presentation, except it's been rotated, so like now it's like, because this is following the IBM textbook convention, because I did this when I was part-time at IBM. But so this is like it's the same globe, but now it's like instead of North and South America facing you, it'd be like Europe and Africa facing you or something like that. So it's like rotated. So the first rule that we're going to see, and the most commonly used rule in the ZX calculus, is you could also call it tensor network contraction, but basically, if you've got the ket 0 state, where's my cursor? Here. If you've got the ket 0 state here, and then you do an X gate to it, then that gives you the ket 1 state. So that's the result. And you could prove it in the calculus by just applying the rule, which if you have only two spiders of the same color that have at least one wire between them, you can fuse those two spiders with the same number of total inputs and outputs and add their phases together. So conventionally, if there's no phase, then this is, if the phase is 0, then you don't have to label it. So this is 0 plus pi, which is pi. And this is the same diagram as for ket 1, as seen up here. Also down here, if you have ket plus and you apply the Z gate to it, then you get ket minus. And you can also, all these phases are modulo 2 pi, because 2 pi radians is a revolution around the circle. So if you also apply the Z gate to ket minus, then you get phase 2 pi, which is just ket plus again. But instead of just this abstraction of just qubit states and gates, you can also do things that are not unitary. So you could do, for example, this copy operation on top here. This one input and any number of output green phase free, so phase 0 spider will copy Z basis states. So if A is here, and throughout this presentation, A and B and any like English letter alphabet, Roman letters is going to be bits. So if 0 or pi phase states, these will be copied by the other color. And on the bottom, this is XOR, or parity. So if you have 2 bits, A and B, then this parity operation will give you A XOR B pi. So this is ket, so for example, if this is ket 1 and ket 0, then this would be ket 1 that comes out. And this gives a nice way to break down the C0 gate as a 2-qubit gate, so 4 by 4 matrix. Instead, it would be just this diagram, where you could view it as first copy and then XOR on these, say, ket 0 and ket 1 states. But interestingly, you could also view it in terms of what it does on the other basis. So this, if you were instead in the plus minus basis, because all these rules still hold if you change the colors, then this would first copy the plus and minus basis state, and then do an XOR of it, but in the X basis instead of the Z or computational basis. So, and this is actually how the CNOT gate can be implemented in the surface code, which is the most popular quantum error correcting code, at the logical level by doing physical operations, which first do one of these and then do the other. So you implement the CNOT gate in 2 pieces in the lattice surgery. We can show our rewrites, but take this copy rule and say you plug in ket0 as the control of your CNOT gate, and copy, and then fuse. And this is a rotation about angle 0 about the x-axis, so this is just identity. Then you can also do the same thing in the opposite direction with the other color. So with CNOT with a target ket plus or ket minus, in this example shown here, ket plus, minus would just be the same thing with pi here. Then you can plug it in and copy. And this is this shows that on the control there's a Z rotation of angle 0, which is just identity. So this is kind of maybe the earliest way we introduced phase kickback to our high school students, because you could see that doing something to the target of the CNOT gate can cause a gate to happen. In this case, not in this example, but if this was ket minus plugged in instead, you would get a Z gate over here on the control. The next rule that we've got, and there's not many rules, so is the color change rule. So we'll use squares to denote the Hadamard, usually conventionally yellow, but my boss at IBM was colorblind, so he like red-green colorblind, so he preferred the blue instead. So these are Hadamard gates. If you have them in every single leg of a spider, then that changes the whole spider to the other color with the same phase. And this is a really handy way to look at the Bell state. So this is the conventional quantum circuit, 2-qubit quantum circuit to prepare the Bell state, which is the most commonly used and studied maximally entangled state. And if you translate all the states and gates one by one to the calculus, then this is the diagram you get. So far, it's just translating. And you could color change the top qubit. So this changes it from ket0 to ket plus here. And then fusion, so this fuses. And since only conductivity matters, and you see both of these are like 2-wire spiders that has 0 phase. So this is a Z rotation of angle 0, and this is an X rotation of angle 0. So these are just identities. So it just becomes this 180-degree bent cup, like this is the final diagram. So you could also look at the CZ gate, controlled Z gate. So this is just conjugating the CNOT gate by Hadamard gates on the target. So do H on the target, then CNOT, and then Hadamard gate on the target again. And this is, if you use those rules, you could change the color of this red to become green with Hadamards on all 3 legs. And because 2 Hadamards in a row, is because these are just like rotations about the Bloch sphere, about the ket Z plus X axis, doing 2 pi rotations in a row, which is what the Hadamard gate is just identity. So that's why you get this symmetric diagram for the CZ gate. So we've now seen enough. We could look at quantum teleportation. We actually, in our course, we look at quantum teleportation 3 different times. So the first time maybe more conceptual. This is more like this. And the second time with just assume that you measured both bits to be ket0. And the third time with all the corrections. But anyway, in the full calculation, if you do a rocket notation, I think the reaction would be that quantum teleportation is really scary. For at least we were teaching to high school students, and in the UK, high school students have 90% of UK high school students has not learned matrix multiplication enough to be tested on it. So in less advanced math courses in UK high schools, it would be like matrices exist, but they wouldn't necessarily be tested on it, and no more than like 2x2 or 3x3 matrices. So here is So converting those matrices and operations to bracket notation could be quite intimidating, which is why we didn't teach it this way for our high school students. But for those who were interested in the translation, we did provide that. So, but in quantum teleportation, the circuit is the one in the top left, where Alice and Bob share this entangled Bell state, the one we saw earlier. And Alice does a Bell measurement, which is like the same thing as the Bell state preparation circuit, but like do the operations in reverse. So C naught and then Hadamard and then measurements instead of qubit state preparations. And based off those measurement outcomes, Bob will classically receive what bits Alice measured and do its Z or X gate correction based off that. But in short, we teach it to our high school students where they only need to know these two rules in the calculus, so just fusion and identity, and how those, as well as how to interpret the diagrams. So taking the quantum teleportation circuit, this one shown on the previous slide, and just translating every step of it one by one, this is the diagram that you get. And then we also, not necessary for correctness, but we added the labels just to show if you're translating it, which part translated to what. And the proof is only a few steps. So I kind of skipped this in the sense that we teach quantum teleportation 3 times. This would be like the 2nd time in our course, but like 8 weeks course, so this would be like week 3 to 5, I would say. So we had the Bell state, which is this maximally entangled state that we saw earlier with that specific preparation circuit. And then once you've fused, you get the Bell measurement. But because these measurements are non-deterministic, so you actually get 4 possible effects that are implemented. And if the case of B0 and B1 are both 0, then this is just the 180-degree wire bent around. And if you do a fusion roll on this red B1 pi with this red B1 pi, you get red 2 B1 pi, which is a rotation about angle 0 or 2 pi, specifically if B1 is 0 or 1, about the x-axis. So because these phases are mod 2 pi, then this is always identity, and that's why you could remove it. And you could do the same with the green, so that a phase of rotation of angle 2 B0 pi, regardless of if B0 is 0 or 1, it also gets removed. And finally, you get just a line from Alice to Bob.
Is there a normal way to indicate measurement in this calculus?
Yeah, the normal way is drawn here. Well, I guess the most conventional way. You could also do something more complicated with mixed state diagrams if you wanted to, but usually you want to measure in a specific basis. So this here, the top one, the green here, is the x basis measurement, and you write it as B0 pi. So the color tells you the basis, and then the bit. Yeah, so this is technically 4 proofs in one, but instead of doing these 4 proofs separately for each possible values of B0 and B1, so those 4 possible values, 0, 0 to 1, 1, then here we do all 4 proofs at once because just to save space, but also you don't. It's the same calculation.
So you write the determination, and then you write in a symbol to indicate the 2 possible outcomes.
Yeah, and by reusing variables, then this is like an easy way to show that you classically transmit, like the repetition of this same variable means that Alice measures B0 and B1, and then Bob applies this rotation of angle B1 pi, or if B1 was 0, this would be 0 instead. So the repetition of variables means that Alice has classically communicated to Bob.
Do you get the same drastic simplification when you do entanglement swapping with ZX calculus, or not as much?
Yeah. So things that I would say in general, the biggest strength of using this is to teach entanglement. So I hadn't prepared entanglement swapping for the presentation today, but I did prepare an activity with C0 teleportation, which is another entanglement example. But I'm not sure we'll get to it, but we'll see. So I guess here, this part of the tutorial is just some TLDR of is that we can kind of go a lot further with this. So one kind of question is this really scalable to like just do these qubit rewrites? Like it's cute, but how powerful is it? And I guess the formulation of ZX calculus in 2007, that was like the response from academics was like, this is cute, but like questionably useful. And probably the big shift was in 2017 when people proved completeness, which in non-technical terms just means, well, the definition is just that any qubit linear maps, so any equalities of linear maps on any qubits, you can always prove using there's always exists a proof using just these 8 rules. So if you have 2 quantum circuits, which are the same matrix that they're implementing, doesn't have to be circuits, but let's just say they're quantum circuits, then there always exists a proof that they're the same using these. Of course, the complexity of the proof will be exponential because otherwise quantum computing would be useless if we could just do every possible quantum computation reasoning efficiently. But for really useful fragments, for example, if all the phases are integer multiples of pi over 2 in the whole diagram, then this is the fragment of quantum computation that's efficiently classically simulable, but non-universal. So it turns out that you don't need really complicated rules to get to all the math that you would need for qubit quantum computing. Pushing this further, in 2023 was the next milestone of not just qubit quantum computation, but any finite dimensional quantum system. So also higher dimensionals for qubits, and then a few months later, any finite dimensional Hilbert space, so any mixed dimensional quantum systems as well. So you could just use rules with these 3 ingredients here. And I won't be able to cover the different applications, but I just smushed a bunch onto one slide and just said, okay, you can see that this can be used across a number of fields. The most efficient way to look up if something of this sort has been used would be zxcalculus.com, which has a listing of over 300 papers, research papers or theses, mostly papers that use these kind of diagrams.
So can I ask you a quick question? So I'm very familiar with the Feynman diagrams. So as you might know, the Feynman diagrams are not just representing the mathematical expressions. Actually, it allows us to compute the particle interactions and photons, electron, and things like that. So if I think of some certain perturbation theory, I can actually think everything in terms of Feynman diagrams and then translate diagram expression into mathematical expressions. So can I use this kind of ZX calculus to draw my own new circuit instead of proving certain identities?
Yeah. So the activity I'll show, hopefully we'll get to, is let's try to build quantum processes based off these kind of ingredients, these fixed gates. Or
any intuition about the quantum circuit identities, just using purely the 8 different rules, I can design the new circuit.
yeah, but the information about the gates, you can further decompose that. For example, the C0 gate shown here and the CZ gate, you could think about those gates in terms of these rules. So I wouldn't say there's separate intuitions. So the next part of this, third part of this talk would be on our high school study, mostly just for people curious about teaching to younger ages as well. So we did a pre-study that we published in the 2023 Quantum Science and Engineering Education Conference. So it's common in social studies that involve human subjects to solicit feedback on the experiment proposal before doing the study. And then a few months ago, in April, we put out the preprint for our paper reporting the results of the study. The experiment was to teach using this quantum pictorial approach in the UK, ages 16 to 18, just test if quantum picturalism, this kind of approach, was effective to teach quantum concepts within the zone of proximal development. So that's the part of this brain image here, that if they can learn these concepts with guidance, so not on their own without any guidance, but not with, or not that they couldn't do it even with guidance. And we gave them a University of Oxford postgraduate level exam, or the questions are from past exams. And so this course has been in Oxford for over 10 years now, and there's also a similar course that has been developed at other universities. And the training regimen was 8 lectures online. So there's a YouTube series of videos that it's now publicly available, and live tutorials with tutors, so online because we wanted people from all over the UK, but based on the Quantum in Pictures book from 2023. So the concepts that we taught in these 8 weeks lectures, notably, we didn't have any mathematical prerequisites except that to know that like different angles, like say 25 degrees plus 65 degrees equals 90 degrees. So that was the only prerequisite that was given on the call, as well as this call for applications to the course, as well as the syllabus. And these applications we also didn't filter based off like any kind of what prerequisites they had or amount of interest. It was just random selection with making sure there's some like balance of diversity in the students. So like say not all from private schools, for example. So, but the kind of topics that we could cover was a lot really ambitious for a high school course. I would say particularly entanglement and mixed state quantum information, we're more able to effectively teach with this approach. We received requests on how to teach this to younger ages. So as young as age 6, we were asked about it, but I don't have data for that. And yeah, but this is a screenshot of Twitter. I think at the time it was Twitter. I'm not sure. No, it's X. I'm sorry. About like the textbook being very well structured by some enthusiastic 10-year-old. This was the flyer. Oh, I should mention, this was a collaboration between University of Oxford Computer Science and Physics departments, Quantinuum, and IBM Quantum.
May I interrupt again? Can you go back to the book, please? So I did see that book, and I ordered it for the library, and you said it's 2023 book. But I think there was, last time we were taught, there was actually a free download on the website, and I just found that I downloaded it, but that's a 2021 book. So is there a difference?
This book is definitely from 2023 to 2024, depending on which country, because it was like Amazon print on demand. There is a PDF now available for free, I think, on the website. But the print version costs money because it costs physical money to print. But there's multiple different. There's like a graduate book level book from 2017, and then there's a new like sequel to that graduate level book now maybe in 2025. So like, well, it's preprint, but yeah. So and this is the like kind of for all ages book, which we've now studied it on 16 to 18-year-olds, but apparently 10-year-olds apparently can also enjoy it and comprehend it, or at least believe that they comprehend it, which is the important measure here, I guess, because we didn't test the 10-year-old, but.
What I have is Coursebook Quantum Theory in Pictures, May 20th, 2021, and it's 97 pages. So it's tiny book.
I don't know of that book, so I'm not sure. I don't think it's related.
And you're saying this one can also be downloaded?
I believe so, but I'm not sure if it's the full version or just the chapters that were in the book. But the YouTube series is public, and I can send the PDF of the book, as well as I think it's on the webpage.
Like I said, I ordered it, but I don't know when it will arrive, and there is a PDF I'd like to take a look at it because it's very pretty. Thank you.
This was the flyer I made, and then someone else edited and made it pretty because my flyer wasn't pretty. But yeah, but we received 734 applications within 3 weeks for the course. But we only wanted like 50-something students, so we, like accounting for retention. So we didn't advertise the course very widely, mainly through school districts and nonprofits in the UK. And I think the main thing we checked for was like ensuring we have ethnic diversity, as well as state schools are the UK equivalent of public schools. So it's like government-free state-run schools. So we have majority of the students from state schools. That's the main thing we wanted to avoid, was like having all the students from the same city or from the same like private schools. And the YouTube video lectures are publicly online, as well as we also did some lectures for Nust University in Ghana. So those ones are also publicly online. And so they look like this. We also had quizzes, so that the students could do optionally, and then with quiz solutions as YouTube videos. And the main outcomes was that, so these were scored, so marked by University of Oxford faculty. So by their standards, so a rubric and then 2 faculty mark, and if there was a discrepancy of more than 10 percentage points, then a third faculty member has to mark it. And we were pretty happy. We were really happy because I was extremely happy because we've been you spend so much time in like study and like don't know how it's gonna go, but it exceeded our expectations. About over 4 and 5 students passed, and about 1 and 2 received a distinction, which is the highest grade category in the UK grading system. So that's above 70%, versus in the UK, 50% is a pass, I think, or 40%, depends. And even, so we filtered by definition question just to check if the students actually watched the video lectures, because we didn't take attendance for, we couldn't take attendance for the lectures because these are just watching YouTube videos, but the tutorials are the live parts, which you took attendance. So it's quite good performance. We received a lot of media attention. There's some more screenshots recently since our April preprints is out, but probably we got a lot of requests after the Guardian article went out. And what's next is, oh yeah, we're close with, or we're the, flagship education, I don't know the exact title. Something flagship education with Elevate Quantum, which is one of the 2 biggest US hubs. I guess recent updates this year, we're doing workshops in the USA, Dubai, Morocco, and Pakistan. The Ghana course is now concluded. The Greek translation of the textbook and rolling out in a lot of high schools in Greece is currently going on, their study. Yeah, and teacher training for Denver Public Schools. So yeah, any questions so far?
I don't know whether you said it. If I draw the diagram using ZX calculus, can you make that circle diagram in a certain Qiskit or Finland code?
There is software to do that. So I guess industry or industry software like Ticket has the ZX calculus, like physics to like quantum assembly language kind of transpiling capability. There's physics, which is a Python tool, open source tool for ZX calculus, and that one also has, you can export and import from QASM. So like QASM is like a broad specification, like IBM. The most popular one is IBM's, which is OpenQASM. So you can do software. Actually, I can show the software now. I'll skip ahead to that. So I guess me and quite other PhD students doing gradware, which is software written by grad students. Our pet project is like ZX Live, which has been really popular with our master's students because they don't like to compute things by hand and they like to just like draw their diagrams, drag and drop online. So this is, so for example, look at this Stern-Gerlach measurement. I won't get into the details, but if you double a diagram, just like how if you have a state vector and you double it, then you get the density operator corresponding to that. And so you can also do mixed, we also teach our high school students mixed state quantum mechanics. So for example, the Stern-Gerlach experiment is like you measure a qubit in the Z basis and then the X basis and then the Z basis again, so non-destructive measurements. And the point is that the existence, like if you repeat the same measurement twice of the same basis, then you get the same outcome. But because you've switched basis, this first Z basis measurement is independent of this second Z basis measurement. And the graphical way we show that is with the Hopf rule, which was something about Hopf algebras, but for the high school students we call it leg chopping, although we also gave the translation for the terminology to them. And this is our ZX Live. Drag and drop, like kind of in alpha or beta, but it works on top of physics, this Python tool for the ZX calculus, so it's a Python GUI. And you can like click and drag. My contribution was making the highlights of the notes. There's also like voice packs and other things, but you can draw this. So this is the ZX diagram, once the connections are made, of the Stern-Gerlach experiment going from bottom to top. Where at, essentially, So essentially, we call qubit wires these two wires in parallel because of this doubling that happens because of density operators, just like you would do outer products of like a state vector to get the corresponding density operator. So that's like two wires in this case for a qubit, versus one wire would be a classical information or a bit. So if you have a qubit that's input here with these two wires going in, and then it goes into this Z measurement, and outputs non-destructively, you measured the qubit here, but you also get a classical bit of information. Let's say it's this one. And then you do an X measurement, and you also get a classical bit coming out of that, which is the measurement. And then you do one more Z measurement. We can go into the video editor in ZX Live and go to start derivation. So, and now we use this magic wand tool, which is, you can also apply rules based off like clicking the buttons for these rules about the names of the rules. But here, this magic wand tool like lets you shortcuts for some of the rules. I messed up. Okay, whoops. Okay, cool. And then you can use the magic wand rule to play like Fruit Ninja, where you cut the legs like that. And then on the right-hand side, it has a proof editor, which shows what are the rules you've applied so far. So we've done the hop rule twice because of this slicing. And then so each rule application is like, you still have the same diagram that's mathematically equal to the other ones. Like if you were to write down the matrix, it'd be the same. But cutting these wires, like it shows that this diagram is mathematically equal to the one that we started with. And the fact that these are disconnected, so this third measurement, the Z measurement, is disconnected like from the first measurement, means that there was no information at all transmitted between them. So this is a graphical proof that of the Stern-Gerlach experiment. So now the fourth part of this tutorial, and then if we have time, which I think we will, we can do some whiteboard Q&A stuff, as well as go back, revisit some of the topics that Thomas covered before. But this is a partner cooperative game. So get into pairs. Make sure between the two of you, you have one piece of paper at least, or like, well, like, yeah, you have paper, pen and paper. If you don't have paper, this is the time to find a partner who has a paper. Okay. I should give some more instructions, even though this is mostly self-explanatory, I hope. Huh? No, don't tear it, Sorry, just fold it. So player 1 is going to be responsible for the top half and should never draw in the bottom half, and player 2 should always draw in the bottom half and never the top half. But the only part that really matters is the beginning and the end. But the middle part, I guess either of you could draw, but maybe keeping to the halves makes it better gameplay, I guess. But the goal here, so this is an example you've seen before, but this is quantum teleportation. But here, this is the resource, this is the states that you start with in quantum teleportation, and this is like fill in the blank of what should the rest of the circuit be, such that the whole diagram is equal to the final thing here, which is teleporting the arbitrary single qubit state kit psi, the thing that Alice had, to Bob. So
Can you explain what the circuits are?
yeah, so this one I intended as an example, but the next one's going to be the real gameplay, I guess. But this is, here is the example from this one, which is I guess the solution. So, so the top half, so Alice or player one can only do those allowed operations, the one in the pink box at the very top. So Alice does a C0 gate. So, and then two single qubit measurements. This is A pi and B pi. The two single qubit measurements are in the top ones in the X basis and the bottom ones in the Z basis. So those are the part of the allowed operations. And Bob is only allowed to do these gates, these single qubit gates. I wrote A everywhere, but A pi just means some bit. And you're allowed to reuse variables. So this is reproducing the exact quantum teleportation circuit. And you could prove via just fusion and identity rules that this is equal to just drawing a line from Alice to Bob. So that's the I guess more complicated example. But
If we were playing this,
Yeah, correct.
Zero. Okay, got it.
And same for player 2, but on the bottom half instead of the top half.
But they get to see what each other is drawing.
Yeah.
Okay.
I forgot the rules.
I guess there's no turn sequence. I guess it's sort of to make a homework problem sheet kind of thing more interactive. But player 1 can only draw those things in the pink box on the top half of the paper. And player 2 can only draw these things in this pink box on the bottom half, within this blue square. You can draw anything you want in the purple square.
Well, what are those? So what is that AP and one is full and another one is clear, like black and white dots on AP. But you said it's just a single bit, but is it a matrix operation? What is it?
A pi is the face of that spider that it's next to. So A is a bit, so it's either 0 or 1. And then if A is 0, then it's face 0. In this case, it's bra plus if A is 0. And then if A is 1, then this is bra minus. So this is a measurement. It's non-deterministic in the x basis. This A pi thing at the top, I'll point. This thing is a measurement, a single qubit measurement. If you get the outcome A equals 0, then this means that physically measurement changes the system. Quantum measurement changes the system, so it means that you implemented the effects of bra plus here if you observed A equals 0. But if you observed A equals 1, that means you implemented the effect of bra 1.
Okay, and then the other two operations that player 1 has, Alice, those are the C0 gates.
Yeah, this one's the one with the control on top, and this one's the one with the control on the bottom.
So, but the first one's the A pi of measurements.
Yeah, A pi and B pi. So these are two different bits for the two different measurements.
Okay, and the player 2 can only do measurements.
Player 2 can only do gates. So this is X gate if and only if B, the bit B is 1. And this is a Z gate if and only if the A bit was 1. So if B is 0, then this is rotation by angle 0. And if B is 1, this is rotation by angle pi, which is a half 180-degree rotation on the block sphere.
Oh, those symbols for player 2 are different than the symbols for player 1.
Yeah, so the player 2's allowed operations are different than player 1's.
Well, they look the same, but yeah, I guess they don't have the second line.
Yeah, so this one is a effect because it has one input but 0 outputs.
Okay.
And then this one has player 2's is gates because it's got one input and one output.
Oh, yeah, so those are the gates. And you said they are Z gates, yes? Then?
Yeah, X, and this is a X gate and this is a Z gate. Yeah, so this one is a X gate. It's an X spider with a one input, one output, and phase A pi. If A is 1, then this is a pi phase, which is the X gate. And if this is a Z gate, if A is 1, then this is a pi phase, which is a Z gate. Yeah. But if either of these A is 0, then this is identity, because it's rotation by angle 0.